Another reason why things are very different on small versus large scales is the well-known square-cube law. Let's imagine we have some animal, like me, and we change the size while keeping all the proportions the same. So exactly the same shape, just enlarged. So we'll give it some length factor r, so we've increased r going from here to here. But if the length is r, how about the surface area? So the surface area, maybe the total amount of skin, is going to be proportional to r squared. Likewise, the cross-sectional area of the legs, the cross-sectional area of the bones, the total surface area of the lungs, any sort of area is going to be proportional to the square of our length factor. But now how about mass or volume? The total volume inside is going to be proportional to r cubed. You can see this very easily if you have a sphere. The area is 4 pi r squared, volume is 4/3 pi r cubed. For a cube, area equals 6r squared, volume is r cubed. So there are going to be different constants out the front, but in any case, any sort of geometry, area is going to be proportional to r squared, whereas volume is going to be proportional to r cubed. Now, why is that important? Well, some sorts of physics depend on the area. For example, heat exchange. To cool yourself down, you have to get heat out through your skin. More skin, the easier it is to cool yourself down. Likewise, the strength of your limbs or bones. Depends on their cross-section. Drag, wind resistance, depends on the cross-section. So there's lots of physics that depends on some area. Volume, on the other hand, that will control the mass, assuming you have the same density. And as we saw elsewhere in the course, most things are going to have the same density. And hence, gravity is going to depend on the volume. Likewise, the total heat capacity, how much energy it takes to heat you up or cool you down. Number of cells, if it's a biology, and many others. So this is the crucial difference. As something gets bigger, the power law index here, 2 and 3, are different. So as you get larger and larger, they both increase, both the area and the volume, but the volume increases more. So eventually, when you enlarge the really big sizes, all the physics that depends on the volume is going to dominate. But when you're on smaller scales, it's a physics that depends on the area that's going to dominate. At some point, what that point is will depend on all the constants. There's going to be a switch over from one mode to another. So let's do a concrete example. Let's think about dropping something. And you've got the weight, mg, downwards, and you've got a drag force upwards. Now the drag force depends on the area, whereas the gravitational force depends on the volume. We're assuming that this thing is of size roughly r. Okay, so what is the gravitational force? Is mg, so g is about 10. The mass is going to be the volume, which is going to be roughly r cubed times the density. Let's assume a density of about 10 to the 3 kilograms per cubic meter. So like water, that's probably typical of most animals because they're mostly made of water. How about the drag force? If you remember, the drag force is a half drag coefficient, density of the medium you're flowing through, surface area times velocity squared. So let's assume a velocity of about 1 meter per second. Call C about 1, density of air is about 1. We'll ignore the factor of a half because this is ninja physics. So that comes out as about the area, r squared times v squared, which is about 1. So now we can look at the ratio F drag over F gravity. It's going to be about r squared over 10 to the 4 r cubed. That's going to be roughly 10 to the minus 4 1 over r. So what's this telling us? It's telling us if you have something with the size of about a meter, so a sheep, say, and you drop it at 1 meter per second, drag is going to be irrelevant. It's going to be 10 to the 4 times less than gravity, so your sheep will drop pretty fast. So don't drop sheep out of office windows, please. How about a mosquito? That's got a length of about a millimeter, 10 to the minus 3. So now it's getting much more equal. The drag force and the gravitational force are much more similar. It will still fall, but let's say you go down even smaller, say to about 10 to the minus 5 of a meter, which would be a pollen grain or a bacterium suspended in the air. In that case, the gravitational force will be less than the drag force, which is indeed why pollen grains and bacteria float around in the air and take a long time to settle. So what you can see is, even though the physics hasn't changed, when you're on big scales, gravity will dominate. Things will tend to fall. Small scales, drag and friction will tend to dominate.